Hello, my name is David Groves from the RAND Corporation. In this presentation, I'll describe an analysis to identify climate adaptations in the water sector in Africa. This material is covered in Chapter 6 of the book Enhancing the Climate Resilience of Africa's Infrastructure, the Power and Water Sectors. As a quick review, this full analysis looked at climate change vulnerabilities and opportunities across the 7 major water basins and 4 power pools in Africa. For this presentation, however, we'll describe the analysis for the Zambezi River Basin within the Southern African Power Pool. This analysis followed 4 phases. The first 2 evaluated how the PETA+ strategy would perform under a repeat of historical climate and then under 121 different climate futures. This material was covered in a previous. This current presentation focuses on the second 2 phases. Phase C, Climate Change Perfect Foresight, looks at how to develop perfect foresight adaptations to a representative set of 6 climate futures. And Phase D, Climate Change Robust Adaptation, which looks at which of these perfect foresight adaptation strategies is the most robust across a wide range of climate futures. This slide presents a summary of the ranges of economic impacts to new infrastructure due to climate change for 7 basins in Africa. Note that the PETA plan does not include significant infrastructure investments in the Orange Basin, so there are no results for economic impacts in that basin. As discussed in an earlier presentation, the climate impacts are small and limited to only a couple of the 121 climate futures in the Congo Basin. Impacts are much larger in the Zambezi Basin and are mostly negative. To understand how adaptations to the PETA+ plan could reduce climate impacts and take advantage of opportunities, we developed perfect foresight strategies for 6 representative climate futures. The selection of 6 representative climates out of the set of 121 is discussed in another presentation. For each of these 6 climate futures, we modified the PETA+ strategy to perform better in the representative climate. Specifically, we made basin-level infrastructure adaptations, such as adjusting the planned turbine capacity, increasing or decreasing reservoir storage, and increasing mean conveyance irrigation efficiency. We also made farm-level adaptations, so adjusting the planned irrigation area, the use of deficit irrigation, and field-level irrigation efficiency. Note that the adaptations were limited to just adjusting the planned infrastructure in the PETA+ plan. This slide now shows how the best of the 6 perfect foresight strategies can improve economic performance in terms of scaled net revenues across all the climate futures. In other words, this slide shows the outcome for each climate if the best perfect foresight adaptation strategy were to be implemented for that climate. The green portion of the bars shows the improvements due to the adaptations. For a handful of climates on the left, adaptation can increase performance over the no climate reference case. For another 15% or so of the futures, the adaptation offsets losses from climate change. For the remainder, adaptation only reduces damage, and there can be significant residual damage from climate change. The consequences of picking the wrong adaptation approach or not adapting at all can be large. The blue bars in this graph show the potential loss in revenue as a percentage of revenue under the no climate case if the worst perfect foresight is selected. We call this regret. The orange bars show the regret from simply not acting or just implementing the PETA+ plan. As you can see, for the Zambezi, there is significantly large impact from selecting the wrong perfect foresight strategy, and also significant impact from choosing to not modify the PETA+ plan at all. In order to select among the perfect foresight strategies or develop more robust ones, we look at the regret across all 121 climate futures for the different strategies. This box and whisker chart shows the range of net present value regret in percentage terms for the PETA+ strategy. The fact that the entire distribution is positive or shows regret suggests that modifications to the PETA+ strategies included in each of the perfect foresight strategies always improves the performance of the PETA+ strategy. We now show the distribution of regrets across the 6 perfect foresight strategies. There is always a zero regret future for each strategy, but some strategies clearly perform better across the range of climate futures. For example, the balance strategy, which I'll describe next, has the lowest regrets in terms of the 75th percentile level of regret. This strategy is optimized for a relatively dry future. The perfect Foresight strategy that increases turbine sizes to take advantage of wetter futures in the Zambezi leads to high regrets over most futures. This next chart illustrates the kind of robust adaptations proposed to the PETA Plus plan for the Zambezi Basin in terms of the amount of PETA Plus investment that is adjusted to be more robust. First, about 85% of the investments in conveyance to the irrigation sector should be modified to increase its efficiency. Next, more than half of the planned expenditures in reservoir storage should be made to projects that are downsized. Only a small amount of storage, less than 5%, should be upsized. Lastly, a bit more than half of the hydropower turbine expenditures should go to upsized project designs, and about 40% should go to downsized project designs. With these adjustments to the PETA Plus plan, significant improvements in the hydropower and irrigation sectors would be realized. In the hydropower sector, these savings could reduce revenue losses from about 18% to 10% from revenues under no climate change, an amount greater than $4.5 billion US. In the irrigation sector, regret could be completely eliminated. The cost of these adaptations are small relative to the savings, only $1.35 billion in the hydropower sector and less than $1 billion in the agricultural sector. We now summarize our finding for the analysis of robust climate adaptation in the Zambezi Basin. First, there are significant potential impacts to the water sector, as we see. Infrastructure plans can be adjusted to improve performance across the range of climate change futures. However, uncertainty makes it difficult to know which adaptations should be made. But by exploring adaptation regret across a large set of climate futures, we can identify robust adaptations that can improve outcomes across the full range of climate futures. To conclude this presentation, I present some limitations and possible extensions. First, it's important to highlight again that this analysis focuses only on large infrastructure. Small and distributed infrastructure may be less vulnerable to climate, more adaptable, and have lower regrets, and therefore really ought to be part of a robust adaptation strategy. Lastly, the information from downscaled global climate models may underestimate the effects of climate variability. In the absence of other information, we believe that the downscaled GCM information was useful to assess vulnerabilities and propose adaptations in this study. However, as adaptations are refined or newly developed and evaluated, it could be very valuable to stress test them again against future climates that are more variable. Thank you very much for your attention.